Can you shut back? Can you shut down the microphone?
Du menar sätta på? Okay.
Maybe we can do the same on your laptop.
Do the same?
Did you change settings?
No, it's just so to Zoom.
Yep.
You have to connect to Zoom, otherwise it's not.
I thought because they don't use the headset. They...
Oh yeah, you need to use the headset. And you need to press audio. That's all right.
Det kan styra vilken kamera. Här på podium. Sen så har den...
Vilken är podium?
Det är alltså nu. Här ser vi inte i den, men det är att det blir på de här. Och de två... Ja, absolut. Och sen så när de sitter och kollar så är det på den här två. Just det, när de sitter där så tittar man mot det här folk. Nej, men sen flyttar det bara dit. Så. Jag tror det är. Det ser vi sen.
Man ser på den.
Ja.
Hur fick ni in den på Zoom?
Den här ska kopplas upp till Zoom som kamera.
Det är du som kan det här.
Det är helt uppenbart.
So, welcome everybody to this defense. Sara Haddadi will defend her thesis, Polymer-Mediated Interactions and Phase Behavior of Polymer Particle Dispersions. My name is Wilfriede. I will be the chairman of this defense. So if somebody is not here and wants to come in contact with me, contact information there. The agenda of today is that I will present everybody first, then the examiner will give a short overview, and then Sara will present specific work you have done, and we will have a short break, and then there will be the main discussion. After that, the committee ask questions, and then the audience and other people can ask questions. And after that, the public part of the defense is closed, and the examining committee will retire to deliberate. Okay, so first of all, I want to present all the important persons. Of course, it's Sara, who will defend the thesis. We had the external examiner, who is Professor Johan Bergenholz, professor at Göteborg University. We are very happy to have you here today. Then we have the examining committee, and on the left we have Johan Englund from Malmö University, Vibeke Alfredsson from Lund, and Per Hansson from Uppsala. We are also very glad you are here. And then finally we have the supervisors. We have Jan Forsman, who has been the main supervisor, and we have Marie Petter, been second supervisor. Yes, and then, yeah, of course, before starting, you should turn off your mobile phones, if you have any. And then I ask Sara if you have any corrections or if you want to change anything. Yeah, no? Good.
We didn't try to correct it.
And otherwise, I give the word to the opponent.
Okay, should we turn this off? Okay, hopefully I can be heard also over Zoom. Delighted to be here today. It's always a privilege to get the opportunity to dig into a PhD thesis like Sara's as an opponent. I want to thank the university and Jan for entrusting me with this job. And I have read and enjoyed reading thesis, read it in quite some detail, and I put together a little presentation here to put some context around the thesis. And I selected, as you see, 2 images from the thesis here, which is from the first paper of the thesis by Sara. And you see these stringy, fiber-like looking aggregates. And these are aggregates of very small particles that we call colloids. And these colloids would ordinarily move around in a liquid, which in this case is water, because of the kinetic energy that the water molecule supplies to the particles. However, here they've been attached to one another, so they do not move around quite as chaotically as they would normally do. And then there's this other image, which kind of looks like an artistic rendition of pretty much the same thing. It's like Sara took a pen and drew this, but it's not, right? This is actually the outcome of what we call a computer simulation. And behind a computer simulation is a model for how these colloidal particles interact with one another. So there's a set of rules that they have to obey, and then the computer tracks them, and they spontaneously assemble into these stringy aggregates. So it's much more a prediction of sorts. I'm not sharing screen. What a rookie mistake. Zoom. Where the down to the left. And no, that's off. I minimized all. Where is it? That's the one.
No,
And desktop 1, I guess. Gosh. What? Team viewer. Oh my gosh.
you have to click on the lock.
Thank you. Oh, why did I choose password? No. Yeah, that's. What? I have to leave. No. That's fine, right? Because I can just do this. Are we good? Oh. Yeah. Thank you. Okay, back to business. 2 images. One is from microscopy, so this reflects reality. The other one, you might think this is just a drawing, but it's not. This is a computer simulation and much more of a prediction of sorts. And I think these summarize, well, not summarize all the content in the thesis, but they illustrate the idea behind much of the work in the thesis, in that there are plenty of experiments, and at the same time, Sara has also done a lot of theory. And these two in conjunction, I think, allows her to look at mechanisms of this self-assembly, among other things. So ordinarily, you would have to stabilize.
very much. And we ask Sara to give your presentation.
No.
I'm unplugging.
Kolla att du har
You
det.
have a comment?
Kolla. Nej. På med den. Ja. Den ska på.
Jag försöker. Men det tar en stund. Jag fattar inte.
Men kolla att du har rätt på videon. Den var rätt, men på mikrofonen. Mikrofonen är rätt också. Ja.
Now you can share again. Share screen.
Can you just maximize it?
You need to
Yes,
find
that
your...
one. But you didn't share this one.
That's right. It's share nothing. It's sharing. No. Why?
But it doesn't appear here.
Hold on. Hold on. Don't give up yet. Wait.
No, I think the desktop that you shared, that was wrong desktop.
What?
When you share, like...
You have to share it, I think.
Jan? Yeah, I know, but if I just stop and then share and then choose that one, because you choose that one.
Ja.
No, it's fine. No? Did you do something?
No.
But why isn't showing?
Start the presentation, see what you get.
Start? Yeah, it's what it works like.
Yeah, that's okay. Remove that thing over there. Okay, can't see it. Inte så lätt för det finns inte här. Use slide. Yeah. Like this. Now you can minimize that one and remove it somewhere. Yeah, good.
So thanks everyone. Come to my presentation. So this is the first correction maybe. I will just present my work, phase behavior of polymer particle dispersion, polymer mediated interactions. So we changed the title, it's long, but yeah, it should be fine with this. So first, I will give a short introduction. I will first give a short introduction on the subject and the. You mean like this? But no, the whole thing. Where is it? Should be.
Hang it on the end.
Yeah. Like this. Oh my God.
I guess. Yeah. Yeah.
So, yeah, this is topic of my thesis, phase behavior of polymer particle dispersion, polymer mediated interaction. So I will first give short introduction on the subject and the usage of the polymer particle dispersion in this particle and polymer particle dispersion can be used in many applications. So, for instance, soft matter, where a structural patterning, forming liquid or solid formation particle is studied, and then especially when you want to compare with atomic scale, which is not obtained or reachable by experiment. This can be compared with molecular scale particle forming different phases, for instance, liquid-like or solid-like. Or particle can be functionalized for different purpose, for instance, in food or pharmaceutics. This can be by polymer grafting, for instance. Also, particle can form in different regime, from dilute regime or to more concentrated to form gel-like material, and in different solvent or even polymer matrix, which then has application in composite and film making, that then the mechanical properties is important in that case. So here, in all this application, polymer mediated interaction between surfaces is involved. So this can change properties between surfaces or between particles. So in my work, we use PEG and polynepom, which are temperature-dependent polymers, and so they kind of change behavior within, depending on the properties of the solvent, the medium, and also the particle itself. So we use polystyrene particle grafted with PEG. So we graft this particle with polystyrene and see study effect of temperature and polymer addition and the phase properties of the dispersion, particle dispersion. In other case, we also study phase behavior of poly-NEPAM solution, polymer, temperature-dependent polymer in like a capillaries, which is created by silica rods. So we study effect of temperature and polymer length and the phase transition. So to study this, we need to investigate the molecular level, what happens there, and then in molecular level, and this can be performed by using experiment and simulation. So mostly the thing that we need to look at is potential of mean force, which is the net interaction between particle or surfaces. And this can be by modeling to study how particles interact and how what is the force between particles. So here you can see, for instance, to have a stabilized system of particle, we need to adjust this barrier height or the strength or length of strength and length of the minima and also the barrier height to have a stabilized dispersion. So this range and the strength is dependent on the solvent properties, the medium, and also the particle itself. So to model this, we use density function theorem, see how particle form, like how we can adjust this potential mean force and how to obtain this. Usually particle have thermal energy, which is kT, and then to prevent flocculation, we need to have create this steric or electrostatic barrier to increase this height in order to stabilize particles. So in first work, we building a polymer-like structure. We use DFT. DFT model was established, which is a powerful technique for modeling complex system, for instance, polymer particle dispersion. This is based on energy minimization to get the density distribution of like a monomers within system. And from that, you can find the potential of mean force. So the system we have is like a planar surfaces to which these polymers are grafted. So then we have a different contribution from entropic or enthalpy terms. So the bonding potential, the grafting potential, we use polymer like a PEG, which is thermosensitive, temperature dependent. So we use a special model for this because monomers usually can be both hydrophobic or hydrophilic. So we have this probability of a state and the degeneracy of a state that can be changed with temperature. So we introduce this and then affect like a contribution from like a surface's external potential. So this was established from density functional theory, showing that this particle interacting at a specific condition of experiment, which I can introduce further, they can form this minima, short range minimum and a long range barrier, which then can show specific properties, which I will talk. So, but to simplify this model and to see how particle interact and how form a structure, we try to simplify model by fitting to a 4-parameter model, which takes temperature, grafting density, surface charge, and also ionic strength, which is Debye length, as takes these values as input parameters. So this is then easy to implement in the like a simulation. So from that, it's easy to, we try to adjust this width of the minimum, how it affects the structure of particle. So we saw that particle interacting with this type of potential mean force, they can form a linear alignment, like a polymer shape structure. And this it was focus of the first work, like building this particle in experiments. To validate it with this, we try to use polymerization to synthesize the particle and see how it forms, how it aggregate, how the particle aggregate. So we use emulsion polymerization. We didn't use any polymer here, so it was pure like a polystyrene particles without graft here. Because of the ionic KPS that we use, it was like so particle could remain stable because of electrostatic repulsion between particle. So, but to see the graft we use and to have particle grafted with PEG, we use dispersion polymerization. So depending on the properties, we could polymerize the particles. So they are polystyrene grafted with PEG. And using like a different tools, we could, like an experimental tool, we could find the grafting ratio of PEG on surface, the zeta potential of particle, ionic strength, diameter of particle, so the polymer PEG per monomer ratio. So particles were synthesized and purified, using different techniques that I try to treat them with gently with dialysis and some other which is included in the work. So the particle was synthesized, and then we did the thermal analysis, because the minimum that is suggested in the model is at high temperature, that the minimum show up, because the polymer is temperature dependent, and at high temperature it becomes hydrophobic, and this minimum appears. So we show the videos here at low temperature, which particles are stable here. So, but increasing the temperature, they start to form this linear polymer type of structure. So, you can see that they are more or less like a linear. But if I go to this, like here, maybe it's more even obvious that this particle kind of, because of the properties that we could optimize using experiment, like a small polymer grafting, like a thickness of the layer should be small to create this minimum, short range minimum. And like ionic strength was quite low to create this long range barrier, and also zeta potential to increase the strength. So to create this type, we could optimize the like a synthesis parameter and could see how this particle form. So we could kind of more or less reach the same structure as was suggested by. So here down there, you can see the images from simulation that is suggested the same kind of a structure here. So yeah, for this specific type of polymer potential of new pores. So this was the first work, and then in the second work, the other work, so we use again DFT, so it's DFT model. It was established from before. So the interesting thing is for particle which are hydrophobic and polymer which is non-adsorbing, usually you can see between particle aggregate because of depletion interaction. If you have it to equilibrate, they form aggregate due to the depletion for hydrophobic surfaces and like a non-adsorbing polymer. And increasing the temperature for polymer type, like temperature dependent polymer, they increase like a progressively aggregate, and because of the bridging interactions. But we interestingly could see that at intermediate regime, this particle, the polymer mediated part, interaction is repulsive. So we used a detailed model here using DFT for like a bonding potential, the same model, but without including this, like a grafting potential. But this was established from before, and then for particle that we had, we could modify this model to add effect of graft as well, and we could kind of like rationalize that particles still are hydrophobic because of the condition that we could see. So still we have, with this graph, still we have a particle, hydrophobic particle, but we add that polymer, free polymer here to see what is the effect, and if we could like create the same properties. So here we have an effect of grafts, both grafted polymer and also the free polymers. It's slightly simplified using Lennard-Jones potential instead of this probability of a state, which is kind of complicated. But instead we modified for the introducing the graft here. So we could see the same thing at low temperature. They form depletion because of the free polymers, which are non-adsorbing. At high regime, they form aggregates, but at intermediate regime, interestingly, the polymer-mediated interaction, because usually if we have free polymer, they either depletion force involved or the bridging, but here, increasing the temperature, we could, at low temperature, we could see that they are stable, and they can remain stable in the system. So we try to see how it works in the experiments. So we did use the same particles, and we added the polymer, long polymers, 100 molecular weight. So we did the thermal analysis, and we kept the particle at high temperature and to let them like equilibrate. So at low temperature, on the left side, you can see that particle like aggregate, which is due to the depletion. On the right side, we could see this is like a severe aggregation due to the bridging, but we could see that particle redisperse in the intermediate regime. On the right side, we could also see what is the effect of polymer addition on the order and like a structural patterning of the particle, where we could see without PEG, they form more like a linear, as this was suggested before. And after polymer addition, like we could see that they are more like isotropic structure. We could also see the evolution of this aggregate, how it changes with day to see, yeah, but they depend because of the model, like they could remain like a liquid-like particle, even though they form grafts, but they, because it's quite dilute at low concentration, like a low volume fraction of particles. So with this, we could also construct a phase diagram depending on the polymer and like a particle concentration. We could see different phases from a singular, like a different, like a branch or more a stable, linear, or like a phase separated dispersion. On the top, you can see the detailed model, but like a bottom, you can see more simplified, but with and without effect of polymer, which is with addition of polymer, it creates more long range minima here. But we didn't introduce the electrostatic, Poisson-Boltzmann electrostatic repulsion here, which could kind of create a more long-range barrier. But it's simplified, but it's like can suggest the qualitative work of the structure. In another work, we used, because for the simulation, some like a normal moves were used, but suggesting that a particle can reach like a metastable plateau. But in this work, because of having this type of polymer, like a potential of mean force, which is kind of complicated to or challenging to use it within simulation, it's especially molecular dynamics, because of this barrier and the minimum, we use Monte Carlo. And then Monte Carlo, we added another move, which is AVBMC type. This is from simulation. So we could see that introducing this move, particle could reach another plateau, which kind of indication of the equilibrium state. So this is mainly because it's not usually reachable in experiment. We could say that because once a large cluster formed, it's hard to move them or like leave particle for particle to leave the cluster. So this is kind of unphysical. So move for Monte Carlo. So, but we could see that they can reach if they tackle this barrier, they can reach kind of another state which is more like stable in that case. But and then they form more, even the thickness and the shape of a structure is create like some Bernal structure forms. But this is effect of this addition, like a move on the structure. Because with this move, we can allow particle to move from the cluster, which is not possible usually. Once they form in experiment, is not easy because of this repulsive force that is between them. So it can't be seen in the experiments, but this is it can be produced in simulation. So to complete like a first work, it was we tried to see what would be the effect, because in that case we studied the effect of width of the minimum on the structural patterning. So we try to see how they form, like how they interact particle if we keep the we change the thickness of the graph. So we did purchase the particle, and then we try to graph the particle using this amine reaction. So we did synthesize the particle. Because particles were quite highly charged, but we could graph them and create different sample of particle and measure the same experiment with thermal analysis. We could kind of measure the zeta potential at low and high temperature for this type of particle. But for the particle that we were interested to form, to see if they form aggregates, for this low and small grafting, we couldn't see any aggregation in the particle, which was due to the high zeta potential that we could get from experiments. So, and here again we use the same model. Here the particle were hydrophilic, so that's the surface was hydrophilic, but due to the large barrier, like charges that we had, we couldn't see any, even though they are grafted similar to what we had in the first work. But here, due to the large number of surface charge, we couldn't see any graph. So this kind of effect of electrostatic repulsion. So in this work. In the last work, we were mainly interested to see what would be effect of capillaries on the phase behavior of polymer or thermoresponsive polymers, such as polynepom. So we did try to create the phase diagram of polymer solution. So we could create at different concentration. We could create the phase diagram of polymer. For capillaries, we used a silica particle to form which kind of form this geometry. So then we added the part like a polymer solution to the particle and try to see what would be the effect of this polymer. This work is still in progress, but we could we use magnetic spectroscopy. So which based on the intensity of the peak changing with temperature, we could detect the phase transition of polymer changing the conformation, and this is detected by within the spectrum. So we could find that this particle, they can reduce the LCSD of the polymer solution, but this is more qualitative work to see if we can see the reproducibility, but we could kind of, for a few samples, we could see that it showed a lot, because this is suggested from the model, the same model, that having capillaries can reduce this bulk LCSD for the polymer solution, which is due to the truncation of the interaction between the monomers, and then due to this surface effect. So yeah, to summarize, here we use like a particle and polymer dispersion to see what is the effect of polymer mediated interaction on the structural and then face behavior of system. We kind of see effect of grafting and temperature on face behaviors. And then we could detect a repulsive polymer mediated interaction in between, like in intermediate regime. And then, yeah, then we could see effect of this parameter on the stability of particles and the phase behavior of dispersions. So I would like to thank my supervisor, Jan, Marie, and Sophie, Patrick, and the rest of people, and also Swedish Financial Support. Thank you for the, supporting us. Thank you. Yeah, and then, it should be fine.
So, thank you very much for this presentation. We now have 10 minutes break and come back at 1:15.
So maybe.
Hello.
Jan,
Come here.
how did you find it?
Except it was good, except the sound is a bit
Was
low.
it noisy?
No, the other way around. Yeah. Hello?
It was.
You can see that you're talking because it says talking on close.
Ja, men hörs det? Hörs det här? I think maybe you need to have the microphone closer to you or something, because it was hard to hear. Or we can increase this maybe.
Yeah.
Let's see now. Johan, you will also be using a headset, right?
Yep.
I guess. I should.
Yep.
For me, it sounded like the microphone.
I started with shaking voice, but I don't know. I hope
That's
I
also right.
managed
Yeah,
to.
So now we
Hello.
stop sharing, I guess.
Yes. But you need to have the computer up.
Yeah, sure. We need to have the
same session. Yeah.
the camera on for the video on from that one. So we need to show the video, I suppose. So.
Yeah, we can also do this one now.
Zooming in on the opponent, then. No?
Yeah, it should be the. But we're still podium. I don't know why it's not moving. That changed. Yeah, good. Oh, yeah, good. So now you have. There's another one which is similar, but no, that's not one. Okay.
Yeah, but how does it look now?
Yeah, you can see it there. You can actually do this instead. So now we have it here also.
Yeah, that's good.
We have one comment here. What is?
Let's see if you can arrange that the microphone comes closer to your mouth.
Let's check this.
Yeah, that's what I know. Actually, we could actually have the chat up, because it means if there's somebody saying something, we can see it here.
Yeah, that is also good.
See. So this is supposed to be like this, and then.
Why didn't I test it?
You have it like this.
Yeah. I could test that before, so.
I think we have one more. Also, you can mute it, so it's not, that was muted.
Jag har mutat.
Was it my fault or? I don't know.
I wouldn't say fault, but
Challenge.
we need to do that first. Yes, this is Chinese puzzle. You need to understand how to mechanics works. I think it's something like this. Yes.
Flytta den lite längre fram. Jag tror det är lite så här problemet.
It's not the most sturdy thing.
Kan man ta den?
Kan man göra med det? Ja.
Yeah.
Ja, det var
Let's
det.
try it.
Ska jag hämta lite tejp?
Ja, kanske det.
If you try and put it on and see if you can hear.
Oh, I started with shaking voice, but I managed to kind of smooth it. I don't know how it sounds. How it sounded.
I guess it was for the Zoomlink.
Yes. Yeah, well, now we have it here also.
It should be, yeah,
Yeah.
as well. It should be, but it's very
Very faint.
muted. Yeah.
Yes, we-
No, it's fine.
Yeah, we like food for to put some sticky tape on it. Otherwise, it was just
No, it
Rele-
should be,
release.
yeah, it's,
Yeah, you should try and listen for
Yeah.
what happens if you talk now and have it in the vicinity.
yeah,
Oh, you don't have, yeah, just talk
like
in.
this.
Yeah.
Yeah.
But is it working?
Yeah, that's one. Exactly.
check volume.
Can you talk again?
So
Yeah, yeah.
it works.
Now it works.
How about me?
Yeah, that's a good question. Maybe I need to do that.
Är du mutad eller?
No, I'm not. This should be working.
There's a hand microphone. This is the headset too. Why can't I increase? I know maybe.
Yeah.
Oh, okay, so the volume was
Yep,
just turned
yep.
up.
Yeah, let's put it up a bit. I think it's
Okay,
yellow. Okay, maybe.
that's probably good. That makes a big difference.
Yeah. Yeah, no, you can. Yeah, you put it on your ears, right?
Yeah.
And then try and push the mic
Yeah.
a bit further close to your
I
mouth.
don't want to do the same thing that I don't know.
No, the other way
No, no,
around, closer
no,
to
I
your
mean-
mouth, if you can.
I think it's fine. Thanks.
Yeah? Yeah, like that, maybe.
Because he
Now you can hear. Now
Yeah, we can hear you. So.
Now it's fine. But you need
How
to
was
bring
it
it.
before? Did
Very,
you have problems?
not this good.
No.
This is good, right? Before it was, I couldn't hear the sound in the loudspeaker.
Yeah.
But you
I
have to
don't
bring
know
it.
what is the
should-
process actually.
Now you have to bring
I
that.
think we should put some tape on it just to make it.
I don't know. I'm not sure. Yeah.
And then you need to bring that to the table otherwise.
Yeah.
Thank you.
No, the other way around. No, like this. So straight up and behind you. No. Perfect.
God,
Very good.
I have to turn this down.
hard process for me.
Yeah.
You can almost turn it down a little bit.
That's a bit, yeah.
Thank you.
Just gonna stick the hole shut.
Ja.
So, welcome back, everybody. And then we start the main discussion.
Okay, thank you. Hopefully everyone can hear me. Thanks, Sarah, for your introduction. I have enjoyed reading your thesis a great deal. It has a lot of interesting things in it. One thing that immediately strikes me, of course, is that it contains a lot of experiments as well as theory, almost roughly 50-50. And which is something I like because of the way I work myself. But it's a bit unusual. So I was wondering if you could just briefly describe how come the project evolved in that way.
Well, it was my work basically started to kind of validate experiment, like a theoretical, theory models. So then we had to test different ways. It's hard to hear myself, but so we had many theory models. So to validate that, we had to test different ways. So I was the only experimentalist in the group. So it was kind of challenging to see if it works different way of doing experiments. But yeah, we could kind of get reliable results from some of them, but some, as you see, didn't. As it wasn't as what we were expected, or we did expect.
So this was actually planned from the beginning. You were supposed to do a lot of experiments.
Yeah, so I was kind of alone to do experiment. I had many consultations with different people too, but it was kind of starting things from scratch and finding the way to do things by myself. But
how much would you say percentage-wise would you have, during your 4 years, have you spent on experiments as opposed to theory or simulation?
I would say 80%,
Okay.
70% was experiment, but I had to be involved in the simulation, kind of. it was like a hard process, but yeah, but it was challenging anyway, doing like a combination or like a stay in between, like a kind of, but
You have to keep your advice. You use polymers a lot in your work.
Mm.
And you have a nice picture in your thesis on page 7, in figure 1.2, where you summarize some effects that polymers can have on colloidal particles.
Mm.
So you have, on the one hand, you have polymers attached to the surfaces of the particles and providing steric stabilization.
Mm.
You have the possibility of polymers bridging from one particle to another. And then you have also possibility of polymers staying in the solvent and providing a depletion interaction. I'm a bit curious as to how you define the bridging in this context. And also what you think is this the entirety as to what polymers can do with colloids?
Well, this is kind of a schematic model for polymers in good solvents.
In good solvents, okay.
Yeah, so, and depending on the concentration, you can reach to like a regime that polymer can bridge between surfaces, but this is in good solvent. For instance, as completion, I added like some notes here. That's how, which was basically the focus of our, I guess, one of the work that could form this intermediate regime. That is recalled that it was created by changing the temperature, which then solvent became like a less good solvent for polymer. Okay. It couldn't dissolve, so this is in good solvents.
So what do you think happens, say for instance, to the steric repulsion then if you now raise the temperature and you make the solvent less good or even poor?
So depending on the properties of polymer, if it is thermoresponsive or not,
let's say
increasing
it's
the
polyethylene glycol.
So that this chain will collapse on surface, and then it doesn't contribute to the repulsion. So instead, hydrophobic interaction will be involved, which cause aggregation of particles. So.
Could you have bridging in that case?
Bridging, so the hydrophobic force due to the bridging can be one mechanism.
Is it necessary, do you think, for the polymer to link, let's say, have one part of the polymer attached to the surface of the bare particle, touching the surface of the other particle?
Well,
or are the
depending
polymers
on the
themselves sticky?
I'm not sure. I mean, depending on the surface properties, hydrophilic or hydrophobic. For instance, polystyrene that we used, it was hydrophobic. So increase in temperature, again, because these chains are expanded towards a solvent at low temperature because hydrophilic, PEG is hydrophilic. But increasing becoming like hydrophobic, then the tendency to absorb to surface that change. But if it is hydrophilic, then we don't need to have this steric repulsion to stabilize particles. The purpose was to stabilize particles, but for this type of surface, which was hydrophobic. So, yeah, depending on properties of particle surface, polymer, and the solvent, these many like a different mechanism can be involved here. So.
Yeah. You know, regarding polymer stabilization of particles, there's some very early work in the 1970s, and there was a reasonable description of the steric repulsion, but when the solvent became poor, you get this collapse of the chains kind of collapse to the surface. And then in those works, they called upon the normal van der Waals force to, you collapse the repulsive steric layer, and that exposes a van der Waals interaction. Do you believe in that?
The van der Waals interaction, it is dependent on the size of particle. So with that, we could kind of, because it's like a index matching, like refractive index matching, which affect the van der Waals. So reducing that can be possible by changing the solvent to match the refractive index, or we added this polymer layer to reduce the effect from polystyrene, because that has a van der Waals effect. But yeah, when with chain becoming like a adsorbed to surface, that becomes more like a dominating force. So.
Yeah, because you use polystyrene particles and have a very high refractive index compared to water, so you are very far from index matching. But I get a feeling that if you've been successful in your grafting, I'm not convinced at all that the normal van der Waals interaction.
For particle, we try to optimize the synthesis parameter to have like a proper size, and we didn't take into account the effect of van der Waals, but that for sure they have effect on the van der Waals. But in the simulation, we didn't consider that. It should be there.
Probably depends a lot on what kind of particles you have.
Yeah, it is established from before. So the model, I don't know what was the process afterwards, but the van der Waals that could have effect, maybe smaller than hydrophobic. That was the main result of the work.
Okay, so you use water-soluble polymers, like polyethylene glycol. So why are they soluble?
Polyethylene glycol, the monomers, usually hydrogen bonding that's with water. And this, based on this like a quantum mechanics calculation, they have some population of hydrophobic monomer because of the isomer rotation, and then and it changes with interaction with water, so stay like at the interfacial effect as with surfaces.
And so when you raise temperature, the polymer becomes less hydrophilic and eventually becomes hydrophobic, and it will phase separate if the concentration is high. But let's go back to the steric. When you attach these multi-particles and you have steric repulsion at low temperature, because the polymer likes to extend out into the solvent. What, in the case of polyethylene glycol, what is the reason for the stability? Why do you get repulsion?
For polystyrene particle grafted with PEG?
Yeah.
Repulsion from?
You have two particles, polystyrene or some other particles. You have a grafted layer of polyethylene glycol, and they
conformational change because of the restricted freedom between these chains, that they cannot it's like an entropy force.
Okay.
So they push them outward. So.
Polymer entropy is one possible component. What about enthalpy?
That depends, for PEG at least, that depends on temperature. But
Okay.
the hydrophobic interaction, they're like, so it could contribute, but maybe it's not dominating, at least at low temperature. It's
Okay.
more entropy that has the effect at low temperature, which then repulse. Because
A lot of people will
they
probably
are
say
at-
that it's actually enthalpy that dominates.
at low temperature,
It's hard to say,
mm,
but before it becomes,
yeah,
before you reach the theta temperature.
Mm. The polymer lens might have effect. Yeah, that is true.
Because, I mean, because you mustn't forget about the solvents. So PEG, let's say low and intermediate temperatures, it's highly solvated, because it can make hydrogen bonds. And you raise the temperature and it, and so if you bring two highly solvated polymers together, it will presumably penetrate, and that means you need to remove some of those water molecules, and that provides the driving force for keeping them.
No, actually, the driving force I know. I mean, I could see exactly what is happening, at least for this graft, which were short. Even at high concentration, they could stabilize particle at low temperature, even at high volume fraction, which, I mean, that's also due to the hydrophobic surface. So this could just, I think it's the main and dominating force. It was like this repulsion from a steric layer. Enthalpy, I'm not sure, so the exact process, but before we could see exactly. So
Well, I mean, you have to, it's the free energy, of course.
yeah,
has to be
minimization, it should be
considered, so it will certainly have an enthalpy component. And most of the time for polymers that phase separate on increasing temperature, you would probably claim that it has to have a large
enthalpy effect. Yeah, energy for sure.
positive component. Normally I would quiz you a lot on the summary of your thesis, but I don't think I'm going to do that today, because you have a lot of experiments and you have a lot of theory presented. And when you go through the summary of the thesis, of course, you treat the theory separately from the experiments. And I don't think that makes so much sense. It's not, at least it's not as much fun to talk about it unless you talk about both at the same time. So I think I'm going to dive into the papers, because there you, for the most part at least, treat both at the same time.
That's, yeah, we try to treat both in a good way. But one thing is, it was mainly qualitative validation of the theory. So it was not like quantity validation, that like in numbers, I'm not sure, but more like qualitative analysis.
So in paper one, you make these, where you look at these aggregates that are elongated, and I suppose the main purpose here is to synthesize these particles, and also look at the stability of the clusters. And you synthesize polystyrene particles yourself, but you're using water as a solvent, and you're aiming for this narrow attraction at short ranges and a long range repulsion. And in water, that's a bit tricky.
It was aimed for that creation. I mean, the synthesis was performed in organic solvent, but the purification that we try to treat them with different method of purification and then change the solvent. So then we had it in like a different solvent. It was dispersion.
Yeah.
So and then the ionic strength, it was hard to keep it low. So, but I mean, we also try to have the effect of these charges with treat them with resin to remove the charges, and then that could kind of increase the stability of particles. So with that resin, but anyway, the ionic strength was low, creating that like a double layer, like a repulsive layer.
Right. And another purpose I gathered was that you want rather large particles, right? So you can see them by microscopy.
Yeah, we could see them by microscopy imaging, like after the synthesis, after treating them.
Yeah. Because for large particles to have a long enough range to repulsion, you need something like a decay length of maybe size of the diameter, and that's tough in water, right? Because it's a polar solvent. So, what kind of decay length or screening length can you achieve in water?
It was kind of radius size. It was in simulation, at least it was like a radius size, like a ripple, like a.
But in the experiments, I mean.
In experiment, we could measure the conductivity. From that, we could calculate the ionic strength. That was 10 to the power of -4 something molar. So, and then we could kind of measure the Debye length. So,
the Debye length, and you can get something like 150 nanometers, maybe 200.
Like a radius size. Radius size.
Yeah, and so it's. And your particles are maybe as large as 200 nanometers in diameter.
Just 180.
Yeah. And that's a tough combination because to have large particles with sufficiently long range repulsion so that kappa times the diameter is actually rather small. You chose to use, and I'm not sure I got this correct. You mentioned emulsion polymerization in your presentation.
That was only a few samples to see the effect of morphology, because with emulsion, the way to graft, it couldn't be like a one-step polymerization. So we could. For polynipon, for instance, we could do polymer grafting within emulsion, but for PEG that we wanted to use, we couldn't use emulsion polymerization, but that was only to synthesize polystyrene without graft and see the morphology effect. But for PEG, we use dispersion polymerization.
But emulsion polymerization has been used.
It's used for polystyrene PEG. For this system, we couldn't use polymerization. But for instance, for polystyrene, we could use emulsion or other type of instead of polystyrene.
So you use dispersion polymerization.
We use dispersion.
So what's special about that method?
The choice of solvent, polymer, monomer, initiator, that depends which is soluble in which. So for dispersion, initiator is like a soluble radical. Initiator it should be fine. It should be soluble in non-solvent or inorganic solvent. So We
Yeah,
couldn't. For
and
instance,
this
for
diagram.
emulsion, you use like a water. For here, you need to use inorganics.
Okay, I thought you used dispersion polymerization because it's usually easier to make a bit larger particles.
For dispersion, because you have like an aqueous solvent.
Mhm.
I mean, even for emulsion, because you have effect of ionic compounds, so there you can have effect of electrostatic repulsion, which can, I mean, it's just a matter of like the choice of the monomer, like what you want, like a polymer. For PEG polystyrene, we couldn't see that would be successful or something,
Okay.
or like helpful.
I noticed that you also functionalized the PEG chains. You did that yourself.
Yeah.
Which I was a bit surprised about because just for PEG, it's readily available. You can buy it and all with almost all kinds of N groups. So I was just surprised that you could find that already made.
So the thing is, as I said, we aimed at one-step polymerization. So we wanted to use polymer as a stabilizer for particles.
Yeah.
So to create this covalent graft, then we had to functionalize. Otherwise, it couldn't be grafted to the surface.
You couldn't just buy it.
You mean polystyrene?
No, the PEG.
The PEG?
With the proper N group.
No, we couldn't.
I see.
But in the other work, we could, because since it was one-step polymerization, we couldn't like optimize or adjust the size of the corona. So, but later in the other work, we aimed at that like how is the effect of this grafting, and then we bought like a particle and try to graft them with another method, but that didn't result in like aggregation because of the high charge. And then particles from there, it was from like an emulsion polymerization could have like a high charge, and then it wasn't help us for the like because there's like a number of charge had to be low for the validation or the like testing the result.
And then on top of all that, you try to make them fluorescent. So you
we
incorporated a dye also in the synthesis. Was that done for all the phases, or
we tried to see like a incorporation of this like a fluorescent dye because of the like a microscope that we had, but we mainly used bright field before, so then like because it was hard to incorporate the dye from in the particles.
Okay.
And then we used the bright field instead of fluorescence field. But we did many analysis, like see how, because the thing is with emulsion polymerization is easy because you have only one solvent. With dispersion polymerization, we had different solvents.
Yeah.
And then it was hard to keep the dye within like a one phase. And then we could leak into the other phase, and then it was hard to incorporate it in the particle itself. It could have been much easier with emulsion polymerization, but this was, yeah.
Was that based on a published recipe?
Yeah, it was. It was based on work. So the process was like from before.
So let me ask a little bit about the characterization of the particles.
But we could get the values that we wanted, at least with the dispersion.
Okay, yeah. And here I was a bit curious about used a number of different techniques to look at the size and the size distribution of the particles. What kind of techniques did you employ?
For the size distribution, we use imaging and DLS.
Okay.
So,
I was actually looking at your supporting information. You quote some average diameters of roughly 200 nanometers or so.
180.
Standard variations of 30 to 50 nanometers. Is that standard deviations or?
Deviation.
Okay.
From imaging, you could samples like a particle, and then you can measure a size, and then from that you could. But from like a DLS, that is based on like a process, which is cumulative analysis.
The cumulant analysis. Well, you can do other analyses as well, but that's a pretty robust one. You mentioned keeping the ionic strength low, and you were working at something like 10 to the -4 molar added salt. Did you mention you used ion exchange resins?
We wanted to, I mean, before synthesis it was different, but after synthesis we treat them to remove that. So we could kind of keep the ionic strength low. And then we didn't, so we could get like a build this linear, like as I said in the first book. So that was building those, so it was easy. But when we try to remove more like charge using this resin, so we couldn't see any aggregation, which as we measured the conductivity and ionic strength, it wasn't changed a lot. So the debye length kept constant, but we could get like a higher zeta potential. From that, we could see that the barrier height is high enough to maybe it's just a matter of equilibration. It could aggregate, but maybe keeping it for longer, like a days or something. But the debye length was kept constant because the ionic strength wasn't changed. Using the resin, at least we could see. But the zeta potential was higher. And the pH was changing, so.
Yes. I was a bit curious. I mean, when you use the ion exchange resin, you just put the resin beads directly into the sample? Or?
Shake.
Did you ever see any bizarre things? Because I have. I mean, I have also, or I haven't. My students have in the past synthesized similar particles. We always had problems with ion exchange resins because the particles would aggregate in their presence.
We work with samples at low volume fraction, so for that maybe for distillation or working with high volume fraction, that might because of other effects. But for at least for the volume fraction that we aim at was fine. We could see that they can't aggregate with that using that. But as I said, the ionic strength that we measured, it wasn't changed a lot even with using that, but we could get maybe the reason that we didn't get the aggregation because of high the barrier height, but so yeah, maybe we could even if we could keep it at the same condition for like a longer aggregation, maybe we could get the same aggregation, but yeah, maybe that's the thing. The purpose of using this is to change the debye length. But we didn't see that much change for the, but we could see no aggregation. So.
You also use dynamic light scattering to monitor the onset of aggregation. At like high temperature.
How the size changes.
Yeah. And you report some results in your first paper in figure 4.
This was from before. Figure
T4, so you have the, let's say the effective or apparent diameter from dynamic light scattering. It's function temperature, and you see a sharp rise in the diameter when you get close to a little more than 70 degrees, or maybe up to even 80 degrees. Do you know if those temperatures, let's call them transition temperatures, if they vary depending on what the concentration of the particles?
Yeah, for sure it changes. I mean, the thing is, PEG has like certain values for like a LCSD that aggregates. But once you graft to the particle, that the particle, depending on the graft intensity, that can change. And the same for the volume fraction of particles. So increasing that, they could shift the aggregation temperature. So that's the process.
Okay. I have some issues with, if I go back to your summary regarding the dynamic light scattering. I thought I'd be nasty and point them out. So on page 38, you have some standard quantities that you deal with in dynamic light scattering. The intensity correlation function in equation 4.3. Right. I mean, I'm not going to say that it's wrong, but it's unconventional. Let's say your denominator looks a bit strange to me.
This is normalization here.
Yes.
So what's wrong about that? Like
what if you make this G2 is a function of tau, which is the delay time. The separation between intensity measurements that you correlate. This function, if you make tau very, very small, let's make it 0. What does G2 become?
The thing is, you need to increase that to see how particle relax. So, but having that, you don't shine light on them, so to see how they behave. If keep that 0, it becomes 1, so it's like a straight line. It doesn't show any.
It becomes 1.
1. Did I say? I said 1.
But normally it's not 1. It's 2.
Which function you mean?
G2, in equation 4.3.
Maybe that's some kind of modification, but here in the function.
You've modified it. Normally you normalize by the intensity, the average intensity squared, not the squared intensity average. That's the starting value. So if G2 normally goes from a value close to 2 and it decays down to 1. If you reach 1, then it's decorrelated.
You mean it's like a sharp too? But I thought it's just a straight line, so it doesn't even, because that you don't shine the light, because tau here, the purpose is to keep it for a while to see how they scatter the light. But
no, well, I mean, you shine the light continuously, and then the detector
but when you
samples the light at different instants in time, and then you look at the time separation between different intensities. And that's how.
I imagine like the function changing, but if you don't shine just the straight line, but it depends with function as well, like.
Well, you still have intensities that are recorded also at tau equals 0, and that's a sort of trivial result. But I'm just saying the normalization there is unconventional.
Well, when I look at the other equation, so it should be like a modification here, because the G1 function that should become like 1. And then from that, you could get this straight line, but
Yeah, I mean, the
Or-
4.4 is fine. That's the Stiglitz relation. 4.7, the cumulant expansion. It seems to me you have an extra minus sign in the first term to the right.
I'm not sure.
So G1.
That shouldn't be there, you mean, from like a because do we wanted to keep the appearance like
I'm just
every
saying
one
that
term? So.
if you have a minus and a minus, that becomes a plus, and then the G1 will increase in time, but that doesn't occur. It's a decrease.
It's the matter. I mean, the values it doesn't change. So, but maybe I'm not sure. But before we wanted to keep it like the way it's.
I mean, in order to recover equation 4.5 from 4.7, you need to get rid of one of the
The
minus.
first one it should be there, I guess. But yeah, I don't know. I'm not sure. But it's the way we adapted from the literature. Like it's the process. Okay.
Yeah,
That should be.
it's not so important. I mean, it's,
Yes, to keep the appearance like a more elegant, I guess, but it should be from beginning, yeah, the equation.
Okay. So in paper 1, you also set up a theoretical model, which is this interaction potential or potential mean force. And you choose two of the parameters, let's say the two important parameters, the ionic strength, and you choose also a surface charge. For the ionic strength, you choose a value which is 4 micromolars, which means 4 times 10 to the minus 6.
After treatment.
But your experiments was different, right? It was higher. So I was curious as to.
You mean the value for ionic strength? I have it in table here. So it's here. You can see. You mean from simulation?
Yeah,
that is very different.
Yes, I mean that is different in the.
The Dubai land and so here we have the 7 to the minus 4 here. So
I'm looking.
maybe one order of magnitude different, but
yeah.
The simulation is from.
It's right after equation 2.
Yeah, I see.
It corresponds to, you get a kappa parameter,
I saw.
and then it corresponds to 4 times 10 to the minus 6 moments. So I was a bit surprised at the discrepancy with the experiments.
Here, 4.
And then also you have.
There's one order of magnitude difference in the simulation with experiment.
Yeah.
But yeah, we did this like the treatment before the simulation, but it should be fine. But anyway.
But then you also have this valence, or let's say the number of charges that you assign to each particle. You gave it 176 negative charges. And that produces a repulsive barrier in your theoretical model, which is quite high. It's something like 20 times KT. And And that makes this study a bit unusual, because I would say most people that work on this type of interactions have mainly probed much lower barrier heights.
Mm.
And actually, when I teach the colloids class in Göteborg, I usually tell my students that if you have barrier heights of, let's say, 25 times kT, it's stable. But maybe I was a bit hasty in making such a statement to my students, because you clearly see aggregation.
We did many treatment. It was, I mean, I could gently treat them. Maybe it could even more like a severe purification with particulate treatment we could be using. Like, but with that we could get enough barrier height, so good values for there. But here we could even, and these surface charges, they could create from ion-specific absorption, or like we changed the solvent, so that was the way to introduce these charges. So within like aqueous dispersion, that is different. The surface are like a, but the barrier height should be fine, I guess.
Yeah. But I mean, this 20 kT is, it almost looks like
I don't know, 80 or 18.
Or yeah, it could be 18.
Even less.
My eyes aren't that good. Regardless, I would consider that very high. So can one understand just very, let's say, simply from this, let's say, sharp, narrow attraction and high barrier and long-range repulsions, why particles form strings?
This is mainly due to the repulsion that has effect, because once they approach the range of repulsion, it's obvious that is the reason to push them to not have this neighbor from the other side. So it's just from the side it adds particle they can add, because the repulsion is there, like removing the other particle to here, the repulsion from this particle.
So if you have a lone particle like here, and you have a linear, small linear aggregate, and it approaches from here.
Once they pass the barrier, they can absorb because of the absorption, but the other one that feels the repulsion from this, and then that adds from the south. Due to the repulsion from this
because the particle coming here feels not just this particle it's closest to, but it also feels repulsion from all the other particles.
Even between cluster, when you create like a different, I mean, when you have aggregates, even the cluster, the repulsion from collective repulsion from particles in each. So not only in like the but it should be one particle too.
So these form these linear clusters, that's quite clear, and you also have the simulations to support this. But that occurs when you raise the temperature. What happens when you lower the temperature again?
In which time this work? You mean just having grafted polystyrene?
Yeah.
They can remain stable even increasing the volume fraction. So due to this steric repulsion, they can.
Yeah, but let's say you work at a low volume fraction, you raise the temperature, they form these aggregates, and now you lower the temperature to room temperature.
We couldn't see like redispersion once they form. It was, but it wasn't reversible, the aggregation.
So it's irreversible.
Yeah, it was irreversible, but once they form, we couldn't see that they could redisperse, but keeping them just at low temperature before forming aggregates, they could remain stable. So
What would happen in your simulations if you did that?
I mean, it's a matter of, it's like a free energy minimization. For us, if it is equilibration, if it is like at equilibrated state, once you lower temperature, they could redisperse.
Right.
If it is equilibration. So, but the thing is, with experiment, we could kind of rationalize that is like maybe it's metastable, they cannot with low, we are having like a reducing the temperature, maybe they couldn't redisperse, maybe that's one thing that we, in another work, we could see like a more stable cluster, even like allowing them for more equilibration. But once they form, we couldn't see at least like that they redisperse. But in simulation, they could.
Sure, yeah, because it's,
In simulation,
if you lower the temperature, the attraction is gone, and
yes.
they will
The values,
separate.
the value for the temperature. We just
But things can happen in real life as opposed to simulations. If you have polymer particles and you raise the temperature up to 80 degrees, polymers, the mobility, chain mobility will begin to increase. The particles become softer. You think this could be a factor in your experiments?
with polymer,
I'm not talking about the PEG necessarily, but the polystyrene chains.
Usually we change, it has this non-equilibrium effect. Once they absorb the surface, it's hard to remove because of the tendency that these chains have with. And maybe that's one reason, but the surface effect.
Polystyrene is...
I don't know, in the whole particle dispersion.
Polystyrene is a pretty good polymer in this respect because it's pretty hard. So it has a
stabilization unit.
No, I'm talking about the polymer that's inside the particles. The polystyrene.
The chains inside the particle.
Yeah. And so when if you raise the temperature to something above 100 degrees, that becomes kind of mushy, and then if you have two polystyrene particles close to one another, the chains can actually interdigitate, and we get a pretty strong bond between the particles. But for polystyrene, that transition temperature is pretty high.
For polystyrene itself, we could use emulsion. So if you have just the polystyrene part, and then you don't have this stabilizing effect from like a chain, so then it's different system. So, but once you have this graft, you change the properties of the like a system. So
I'm just trying to think of things that could cause this irreversibility. Van der Waals subtractions would, I guess, be enough.
Yeah, van der Waals, that could be like it will have the effect.
Yeah. But it's clear from you make a fractal analysis, you extract fractal dimensions, they're very close to one. You have nice linear stable aggregates. And I guess it's practical if they stay together in a sense also. You can collect them and actually use them as building blocks, like I was alluding to in the introduction. In paper 2, you continue with this kind of study.
The process of like the mechanism is different in what I see. But
Okay.
Like in paper 1, we could see they could aggregate like a more like a problem. Like we could build this polymer-like cluster. So in simulation, that is easier for sure to analyze the cluster to create this linear fit or something.
In paper 2, you explore the effect of the range of attraction. But again, you have this quite high barrier, 20 kTs.
The guideline.
Well, it's not just the Dubai length that sets the overall range, but you also have a very high, let's say, apex or the maximum there is quite high.
Very hot.
And in your simulations now, you have this possibility, because it's Monte Carlo, you can make unphysical moves, moves which particles in a dynamic simulation, like a Brownian dynamics or something like that, wouldn't execute. We can move particles across the box, and it's perfectly legitimate to do that. You make two such moves, these unphysical moves. You have this aggregation volume bias move, which is extremely efficient in speeding up equilibration. But then you turn it off, and what you see in the simulations, it's in, let's see which figure is this. I'm thinking about the energy, how it evolved, the potential energy as it evolves.
Yeah, introducing move is just reducing the.
Yeah. It's in figure 3. And then in figure 3, you have one curve which does not have these very efficient Monte Carlo moves. But even so, you get a very rapid decrease in the potential energy after only a few cycles of the Monte Carlo code. And then it levels off to a plateau. So I'm talking about the first curve there. What's going on there? Why does if you forget about the aggregation volume bias moves, why does it decrease so sharply in the beginning?
So the thing is, this move is efficient for system which have aggregates in. So, and with system that have this type of potential mean force, which is quite challenging. Because so you need to use like a pre-equilibrated system and then introduce this move. And then once the cluster move, because it's hard to move them, and like particle is quite, because as you said, it's like unphysical, so you force the particle to exit the cluster. So, and then you kind of you can find different state of formation of like aggregate formation, and then it reduces the energy, but because it's not like what is happening in experiment or something. Once the cluster moves, because then they cannot usually leave the cluster, but this is just you force them to with kind of with this bias that you introduce, you allow them to leave the cluster. So this is efficient for that type of PMF, and once aggregate form, you can introduce this move.
Because you have this other move where you just randomly pick a particle and move it a large distance. Normally in Monte Carlo, you just move them locally.
It's more like a displacement.
But this large move, I guess, in the very beginning, I guess you start from well-separated particles in the very beginning.
That can't be efficient, this type of move. The other moves that could be, because once they form aggregates, then you can add this move.
Okay, I thought this
for like a random guess type of that is not efficient because you don't have cluster form, because this is to detect like a neighbors of the particle, and they should have kind of neighbors too.
Okay.
But it's just
I mean, I would assume that when you reach this, the energy goes down, then it reaches a plateau. Now you form clusters, and now you're basically particles will have to find the ends of those clusters to make them grow further, and that's just very unlikely unless you have this this aggregation volume bias. I guess.
Nice. Once aggregates form, I guess we can use this type of simulation.
Mhm. Anyway,
Even in other work, when you just add other moves, you can just see the transition of this energy. But with this one, I guess it should form some, it should exist some aggregates to remove or like.
I don't know how carefully you examine these simulations, but I was curious to find out whether once you have a cluster, could be one of these very stringy ones, the one that has a bit thicker strands. Do you ever see particles move along the cluster? Can they, or is the cluster completely rigid?
The moves, we introduced these moves, so it's not like molecular, and it's not like dynamic too.
I know, but
you just
since you have this local, you also make these small scale moves. So I would assume the particles, if they're in the attraction, they might be able to find their.
And it can like reach or like approach the other part, but the move that you introduce is just random move, so they can find the more probable states or like depending on the energy of the particle that they have.
Because I know from experience that with, let's say, similar potentials but lower barrier heights, it's very characteristic the fact that you get surface motion. You get like a rigid backbone and then particles moving.
Then you don't have that repulsion, you have smaller.
You have much smaller barriers.
And then when you have this repulsion, when you move particle, you don't allow particle to remain there. If you feel that and like a repulsion, then you remove, like you move it to the sides.
Yeah.
So.
Okay. And it's very clear. I think you do a nice job of establishing that the range of attraction is governing the thickness of these strands. In the third paper, you introduce extra polymer. I'm looking at paper 3. You have, we're back to the peg grafted particles, but now you add extra peg to the solution, so unattached peg polymer.
Like a depletion effect?
Yes, definitely. I'm quite convinced of that, at least at low temperatures.
No, I mean, it's like this intermediate regime to find how validate that if it could be the case even in experiments.
Yes.
It should be.
And you've, again, you use particles. I'm not exactly sure if they're the exact same particles as in the first study, or
we use the synthesized one.
Okay.
So before we synthesize, we treat them, then we introduce how they behave.
Yeah. And here again, you went through characterization, you measure the zeta potential, for instance, and you find very low value. So it's only minus 3.6 millivolts.
And what page?
This is in paper 3.
Zeta potential should be here.
It's top of
here I see.
left, above figure 1. I mean, normal values for colloids, you know, like 20 millivolts at least, even if they're maybe 10. If they have some polymer on there, occasionally if they're extremely dense grafts, you can probably get.
Yeah, with emulsion you could get much more like larger values of zeta potential, but with dispersion you could get this which was maybe the main reason that we use dispersion polymerization. Yeah.
I mean, it's so low that I'm wondering whether is it really different from zero?
The zeta potential?
Mhm.
You could have, for this type of validation that we wanted to create this barrier, right?
Mm.
So we needed to have some strength for this potential. So otherwise it could have this repulsive barrier with zero potential. But
Yeah.
with some values, some magnitude, you can increase this barrier height to have the other length, which is just ionic strength. But the barrier height that should be there. I mean, you can reduce that with some kind of effect, but yeah, even further, they could just remain stable. But for the system, we wanted to keep it low enough. So.
Yeah. I mean, it's, I mean, determining very low values close to zero, right, is usually quite hard. It's quite difficult to get reliable estimates for that range. Okay, so you add PEG polymer and you choose 100,000 grams per mole. And you have a published phase diagram, or let's call it a phase diagram. Figure 2 in the third paper, which you showed in your summary also. And you see from your confocal microscopy, you see a variety of aggregates. Some are linear, or at narrow range you find linear, and then you have more branched ones, depending on the concentration of these added PEG polymers. And then you have metastable and two-phase dispersions. I'm a bit curious what you mean by two-phase dispersions.
Well, it's more like when particle phase separates, then you get like a different phases, liquid and like more, when particle sediment, you can get like some kind of solid like phase at the bottom of the cell, and then you have like a more like liquid phase which contains some, depending on the condition of the, can have some like a gas-like particle or something. But once they've sediment, when you treat them by adding this, then they form this.
That's what I'm wondering about. Is this particles aggregate? Polystyrene has a slightly higher density than water, so aggregates will accelerate sedimentation.
Sediment, no. I mean,
is it just sedimentation of aggregates, or is it? Is there a phase? Do you think there's a phase transition that triggers this? What you just mentioned, liquid.
The thing is, you need to see them, visualize them once they form aggregate. Depending on the, amount of, like a volume fraction or whatever that. You could have different states. They can coexist. Maybe once they become bigger, then you have the gravity which causes them sediment. So.
But what if you could
maybe
density match
we
them?
can't visualize the transition, maybe. But,
But what if you could density match them? What would you
we density match different solvents, you mean?
Yeah, I just pretend that you could do that.
The density match usually is for attraction between particles. You reduce that due to the van der Waals.
No.
Density match for the sedimentation.
Sedimentation.
Then
So all your aggregates will
they
be
may coexist.
floating around.
They may coexist with some kind of.
So it's hard to say, right?
It depends how to equilibrate without sedimentation.
Yeah, I mean, the dilute suspensions of aggregates, it's it's tough to characterize
Yeah,
precisely.
I thought you said reflective index.
No, no,
Yeah,
no.
density materials.
Are the linear clusters expected here in this case? I mean, in these
With this low grafting,
No, I mean with the depletion attraction.
depletion is quite long range. We couldn't see, at least for because the polymer like a length should be high enough to create this, at least to be visualized. With this type that we use, we couldn't see a linear line. It was more like isotropic.
But I mean, you have some in your phase diagram. You have
figure. You mean 4?
You have figure 2 in the third paper.
Yeah, but if you look at like a figure 4, you can see the effect of like a before on the left side and the other.
Yeah.
So that is the effect of polymer addition. So before they form this.
Right.
I'm
sorry.
Kind of due to the long range of, and then this is from simulation you could see the same thing, but you have this more long range attraction like due to the depletion.
No, but in figure 2 it's at room temperature. Figure 2 is at room temperature, right?
Figure 2.
Figure 2 is this phase diagram.
You mean, so keeping the volume fraction low enough, that might be. But if you see it's very small region,
right.
It's very hard to detect.
Okay. Because with a 100,000 peg chain, I'm wondering whether the range of the depletion attraction is it. Because you only expect the linear aggregates for narrow enough attractions, but it may be you have large particles. 100, I bet that wouldn't be much more than.
But as you see, it's more stable.
Maybe not even 10 nanometers in gyration radius.
I mean, it's hard to detect them. It's like because you go from the stable states to that region, and then you get the phase transition, like this aggregates. But we could at least visualize some sample.
Yeah. And then you see this intermediate redispersion, which is
repulsion.
Clearly, when you add the polymer and now you raise the temperature as well, and you get the surprising redispersion.
Like a repulsive polymer-mediated interaction, which was quite interesting too.
Yeah, and I think here the theoretical modeling is absolutely pivotal. I mean, if you didn't have that, I think it would be extremely difficult to explain this phenomenon.
Yeah, that is quite complementary analysis, like
I would say so, most definitely. And I think the DFT monomer density profiles that you provide in figure 5 are very.
I mean, it's interesting to see this repulsive, intermediate repulsive interaction, like repulsive polymer mediated interaction, but that was in a sense interesting. But we needed theory for sure. To explain this, how it behaves. Like.
Yeah, and it's. You explain it by having the particles, well, what you thought were non-absorbing polymers are actually not so non-absorbing anymore. So they actually, you produce a pretty homogeneous polymer concentration even in the gap between particles.
Yeah, I mean, we visualized this for years. It's from before, but it was non-absorbing like before, but it's just it's a matter of it's like a surface effect, how it equilibrates with surface. And then it was like the particle we synthesized, we could rationalize that it remains stable, hydrophobic, and then you add non-absorbing to make a mediate.
I do have one question in connection with that.
Because the thing that it was required to have them hydrophobic surface. So,
right.
So,
For the
even with grafting, we could see they still remain hydrophobic.
Okay.
And then we can see this trend.
Because you introduced the potential between the polymer, an attractive potential between the polymer and the polystyrene particle surface. What if you had a much better coverage of the polystyrene surface, so it was completely covered by PEG? Would this effect be present?
You mean if we add more PEG?
No, I mean
the surface coverage, you mean?
I mean the grafting density, if that was very high. Would you expect this to?
That is different scenario. It's like with even more grafting. Then even the stabilization even different. At high temperature, even maybe steric or.
So this requires that the
the thing is, you need to have hydrophobic. You need to have a hydrophobic with small grafting. The polystyrene is hydrophobic. With small grafting, it still remains there because in this regime, it can. I mean, if it is just hydrophobic, that it might be same. But even with having this grafts, it remains still stable. But adding more, it may reduce the hydrophobicity. So, and then you might not see this behavior. We wanted to have it, I mean, hydrophobic. So.
Yeah. Okay. I think it's a nice finding, definitely. Plausible model, but it seems to me that you need to have grafting density must not be too high. You must be able to have some.
It might reach the hydrophobic surface to be hydrophobic.
Let me see if I have something on the last paper. I was. Something struck me when I read this the first time. This is the paper on capillary-induced phase separation, which is a purely theoretical study. And you have a rather simple model. You have A and B monomers and a solvent, and you introduce surfaces. I noticed something. You use Lennard-Jones interactions for all components, and you found a combination of Lennard-Jones parameters for this mixture that gives rise to an LCST, lower critical solution temperature. One of the energy parameters is the mixture is negative.
Which
the D monomer interaction with the solvent.
Yes.
Yeah.
Because it's hydrophobic with solvent.
So is that physical?
I mean, we introduce because you have different population of monomer, hydrophilic, hydrophobic. With water, it's repulsion between them. So you have that.
Yeah. So right. So you have with a negative energy parameter, it becomes repulsive at long range. Then I was just looking at the equation 3, which is just the ordinary Jones potential. So what when you make epsilon negative, what happens to the repulsive part?
This is relative, so you have like a relative effect for repulsive or like a repulsive or attractive, and so you sum over this interaction. So if it is like inert is 0, if it is like hydrophilic or hydrophobic, this you change that, so it's relative effect. And that is the epsilon.
But I think epsilon here only
it's like a magnitude.
applies to
it's the magnitude.
Yes,
K3.
it's the magnitude, but it's the magnitude only of the long range part. The short range part must be in the DFT theory treated separately. So I'm sure it has to, the excluded volume is treated in the first parts of your DFT expression.
I mean, if you look at, the first term, you can see that it's even the short range. Yeah, it may have effect on the long range parts.
So this is only the long range part that this applies to, and then I think it's fine, or you can have a repulsion.
It's like a relative, and then
between monomer B's and the solvent. You do something in the appendix, which is also a bit interesting. You replace the surfaces that you introduce, which were originally composed of B monomers, the surfaces that causes this capillary phase transition. You replace them by hard particles, and you call them inert. But yeah, I don't know if I would
you mean, yeah, then there is no interaction between.
Yeah.
So,
But in this case, with this mixture that you've set up,
I mean, that is just to be compared with the first what like before it's Leonard, and then you introduce this,
but I suspect that the hard surfaces will still be solvophobic. Because
it should be like a more repulsion from there, and then you see the density distribution is different. It's even more broad there if you compare, because the Lagrangian potential that has like a short range effect, and then due to those power, but here with no interaction, then even the like a shape of the that is different. So.
Yeah. I was sitting on the train yesterday, and I hadn't actually read the very last part of the summary. I figured I'd focus on the papers, but there's a whole section in there that covers experimental work that did not end up in the papers.
It was
5.5.
helpful to see what would be result of this experiment, but it wasn't worth maybe.
I think that's great. I always tell my students that this is your opportunity to put in things that didn't make it into the papers, and it will still be helpful to a lot of people. And in your case, I think it's a pity that you didn't put some of this in the papers, or maybe write a separate paper. In particular, this synthesis where you post-graft the carboxylated latex, you attach peg chains, you put them in your DLS apparatus, and you measure the zeta of the tension. the carboxylated latex are strongly negatively charged, but when you attach the peg chain
from emulsion polymerization.
Yeah, they become positively charged. Or you get a positive zeta potential, I should say.
The thing is, we added like this grafted polymer that had some. We tried to see what this affected with. We weren't sure that it is the real like effect of PEG, but we know because this the synthesis is performed at low pH, so it might be like a side reaction that causes this amide form, and then that it might be side reaction, but otherwise it's neutral.
This is from a published recipe somewhere.
It was from one like a Stratner.
Anna Stratner. So did she also observe this?
They didn't use it for this purpose or measured. They had further use for protein absorption, that specific, but they refer to the purification step, how you treat the particle. That was quite sensitive step to see and to be able to graft the particle. I don't know how reliable is this, the results in this work specifically, because it needed to be like a well purified for particle before, because you have the particle, you purchase the particle and then you graft them, but before that you need to do the dialysis to have them purified, and then we might have some non-grafted polymers still at the surface. That's the effect. Otherwise, if it is just grafted PEG, that is not sure with no sign, but with no charge. But we guess that it should be effect of non-adsorbed, non-grafted polymer there. Which is due to the side reaction at low temperature, at low pH. We're still not sure, but.
Well, it would have been nice to find out, because otherwise you have a pretty, I don't think I've ever seen anything like this, because then you raise the temperature and all of a sudden the particles become strongly negative.
Because that's the thing, either the external layer approach to the surface showing these charges, or as I said, it might be some non-absorbing polymer and then because the surface is hydrophilic, and then once this polymer becomes hydrophobic, it detaches the surface and then they form some kind of maybe glob, and then the size, and then it's just maybe the whole grafting wasn't successful or something. There are some scenarios here which what is the real mechanism,
But I suppose, in electrophoresis, you don't, strictly speaking, you don't measure the charge, you measure how mobile the particles are. And it's pretty reliable technique for, either the particle goes towards the negative electrode or goes to the positive electrode. So,
it's changing.
It's hard to think of an explanation, but I think it would be a very cool system to have it.
That's the thing.
Temperature can simply shift the sign of the apparent.
It's a matter of absorption or grafting, if it is grafted, or if it is absorbed.
Yeah. And then on top of that, you have other systems that you have done as well. So it's clear that a lot of work has gone into this work, and I think you should be very happy with it. I am finished. Thank you.
Thank you. Thank you. I'm not sure that it was helpful to do this.
So, thank you very much for this discussion. Then it's time for the committee to ask questions. And let's start from this side.
Okay. thank you very much for a very interesting discussion and reading. I very much enjoyed it. I think your opponent has penetrated the book very thoroughly here. But still, I always like to visualize things in a more engineering manner, just to see what do I have in front of me. And then I'm thinking about the sizes of your different components and how you synthesize the particles.
The synthesis?
Yeah. I mean, you have your styrene monomers, and then you have a macro.
Well, it has to do with parameters, so you could change different parameters to optimize the size. So we could change the rate of measure, like a synthesis, but the amount of polymer you add, the amount of whatever component, it could have the effect. So we change the amount of polymer and the rate of this, stirrer. So
yeah, but you add all the components in one pot, and then you.
It's like a one-step polymerization. That's true. And then we use polymer as a stabilizer, like a PEG as a stabilizer.
Right. Okay.
Because, for instance, because the initiator that we use is neutral, so it doesn't have effect on the stabilization of particle. But the polymer, because there's once this nucleate form, they are hydrophobic. So within some kind of solvent, you need to keep them stabilized with contribution of PEG, and then also the refractive index matching, which is the choice of solvent. So these can have effect.
So you emulsify the styrene particles in the solvent?
No, it's not emulsion. So we did use dispersion polymerization. It's not emulsion.
Okay. Well, I'm not an organic chemist. I will not question you on
the thing. Even is different from emulsion. Emulsification is different. So with polymerization, the name of emulsion, for instance, has something to do with the polarity and the hydrophobicity of with what phase they can dissolve or something. So for emulsion polymerization, we use different compound, which should be like a polar or like an ionic.
Right, but the final result, which you are very sure
Dispersion.
about, is that you get the polystyrene core and you get the PEG.
The PEG crafted.
Then you have this rhodometer. And I'm working with lipids and surfactants, which are smaller, and then dyes are huge. If you add a dye, you completely convert the system and get different properties and stuff.
Yes.
You don't have that big risk here, but the dye is still quite big, right?
You mean
in size?
In size, we didn't see that much difference in size once you add the dye.
It's a tiny amount.
It's a small amount here, that's true, but the thing is, since you have different phase, like a solvent, which is like aqueous, non-aqueous, it was hard to incorporate into the polystyrene itself. With emulsion, it was easier because it was just one solvent there, and then down you could have polymerizable dye or hydrophilic dye, then you could kind of specify and incorporate it in a specific phase. But with dispersion, we could use different solvent. It was hard to just keep them in there.
But the dye you used was polymerizable as
well. It was
So
polymerizable.
was that a separate chain?
If it wasn't dissolved in the inorganic solvent, which was that's the thing.
So you don't know exactly.
It wasn't that strong effect that
Yeah. Well,
because if it was water, for instance, hydrophilic phase, we could have for sure push them into the particle, but having other solvents in the system, we couldn't kind of get efficient incorporation from it.
this was more from my curiosity, and we discussed yesterday that committee members tend to extend the discussions this day, so I'll try to keep it shorter. But talking about geometries, you have a macromere MPEG of 2 kilodaltons. How many monomers is that, and how long is it?
44 monomers. It exists in that polymer.
So how long would that chain be roughly?
It's 4 angstrom or something. So it should be like a 40 nanometer or something.
Yeah. Well, 4 angstroms per either 4 or 5.
You mean the size?
So the whole length of your chain would be something like 250.
This is based on the quantum calculation. It's like a length of extended in like in a good solvent case, but it could form different conformation. This depends on the process. So.
But if you would stretch it,
yeah, if it's stretched at the longest 40 nanometer.
And in your paper 1 on page 674, you report a thickness of 42 angstroms, so it's not extended, it's rather compressed, as you discussed before.
I'm not sure.
Yeah, the interesting thing with PEG is that you would assume that the PEG of this size would be liquid, right? So the melting point is rather low.
The thing is, we have it in solvent, we don't have it in polymer matrix.
Yeah,
because when you have polymer matrix, you melt like a PEG, but you just dissolve it so you don't have polymer matrix here. Like it's like aqueous dispersion, because you just dissolve.
Since you mix PEG with something, or if you mix 2 components, you normally get a decrease in but now I happen to have been working with cleans, polysorbates, so non-ionic surfactants, PEG-related non-ionic surfactants. We saw in one of our papers that if you go below 5 units, the PEG change doesn't crystallize. But if you go up to 10 units, you can actually crystallize the PEG chains on that surfactant, even at room temperature. And then I found a related paper, because of course you start to dig where you are yourself, and since I came from that direction, I found a paper in Nature Communications from 2018. They talked about block copolymer crystosomes. So crystalline somes, you have liposomes, you have tubosomes, and they have crystosomes. So they had a polylactic glycolic acid core with PEG 5000 as
what was the process? Was it like a particle synthesis or like emulsification, even with emulsion? Like before you said something, what was that? Exactly?
Yeah, well, it's a block copolymer chrystosome, they call it. So they have a core with polylactic glycolic acid instead of your styrene.
Yeah.
And then they have a shell with PEG, but slightly longer than your PEG. And they say that the PEG shell melts.
They use different process, you mean?
Yeah, I'm not talking synthesis now. I'm just talking the particle, which I think resembles yours. And they say that the shell, the PEG, melts at 45 degrees. And then I'm thinking about your stabilization. I mean, it's one thing that you have the clouding phenomena, you increase the temperature, it becomes more.
Yeah, I see what you're saying.
And then it sticks together.
No, I'm not sure, but the thing is, before doing synthesis, like the process before that, you need to dissolve it at high temperature, you treat them. So you increase the temperature, you do this reflex to just like dissolve them kind of. So before going to the step which is synthesis of particle, you do this treatment that you need to this increase temperature to easily dissolve this PEG. And then once you have it dissolved, you decrease the temperature and you add monomer to proceed the synthesis.
Just just to minimize the question a little bit. If you have your particles, so forget about the surfaces, they are all done.
Yeah, actually.
The particle is there. You have your peg on the surface, but you say that you have to heat for them to attract. And then you say that you have long-term stability. And long-term stability is after going back to room temperature.
No, it's before synthesis, so you need to have a peg dissolved in water. So peg is hydrophilic, so increase the temperature is even it makes it easier to dissolve. So once you have it dispersed in water, then you add monomer, which is hydrophobic, and then they grow, and then this is kind of like a protective layer staying outside the particle to just stabilize particle. This is the treatment, like a core, it's like a what happens is when you have surfactant. It's like a stabilizer. So
I will not press further on this, but what I wanted to come to is just a hypothesis. I don't know if this is true. I'm just speculating. But what would happen if you induce attraction by heating and changing the properties of your peg layer, and then when you go back, it kind of solidifies and stay entangled? Is that could that be the mechanism of your stabilization? Would be my question. And I have no clue if it's true or not.
I'm not sure if it is. It should be. I mean, the thing is, increase in temperature. It facilitates the dissolving the polymer. But I don't know. I'm not sure about this. Like,
think about it.
the thing is, you. No, I know exactly, but I mean, if it is melting or solidifying, you mean?
Well, I think that for future studies, maybe you could use different pegs and different chain lengths and study the phenomena in a similar way and see what
the thing is, we didn't even use the peg itself. We functionalized for a specific purpose. So before experiments, so it has like this side group, which is hydrophobic. So that does have effect. I know what is like this characteristic temperature for the process to kind of facilitate the synthesis. But we did the treatment before temperature. So we create this side effect to have it hydrophobic. Even with that, we could kind of stabilize particle. That's not the case. Like if it is like a solidify or melt, it's not. I'm not sure if it is true for my case. So. It should be something with process, different process.
Thanks a lot.
Thank you very much.
Can I continue?
Yes.
Okay. Thank you, Sarah. I think you have done a lot of work, as the others have already said, and you've written a really nice thesis. And you have, I think your illustrations are very good, very pedagogical. I have a question regarding one of the illustrations, and this is on page 6. So here you talk about polymers, polymer absorption on surfaces, and you talk about 3 different types of conformations depending on concentration of the polymer.
And the surface properties.
Yes. So you talk about the pancake, right? Mushroom.
The brush.
And brushes, and that is as a consequence of an
increasing.
Yes. So I guess with brushes you get more
extended
onto the surface. But why don't you get a stack of pancakes instead?
So here, let me think. thing is, for pancake, the polymer is absorbing the tendency towards surface in that case. But in the other case, we didn't refer to any surface like a hydrophile, like a surface tendency. So it's non-absorbing there.
They
but
all absorb to more or less extent, right? Also the mushroom.
yeah, but it's not like that because it's written here that for that type of absorption, it has something to do with surface tendency. That if it is, but otherwise it's non-absorbing.
Isn't your graph showing the same kind of polymer, just different concentration of the polymer?
Mm-hmm. It's we refer to both concentration and polymer like a tendency towards surface.
So you mean that
in that case, it's just concentrated concentration that matters.
Yes. So then I don't understand why they can't stack a stack of pancake instead of.
We have written here that if monomer have tendency to attract to the surface at low concentration, but even based on the references, we don't see many like reference to the pancake regime. It's usually either maybe but this is something to do with tendencies toward absorption. Yeah, but otherwise.
So maybe they don't. The polymers, the absorption or the attraction between polymer is smaller than the attraction between.
That's something.
Yes, so okay, thank you. Then I was wondering if you have these. I mean, you have these spherical particles, right? Graph these polycylin particles grafted with peg, and you get these colloidomers.
Like building.
Yeah. But you have spherical particles. What if you didn't have spherical particles? If you had even particles?
Inherent properties, I guess. That's like many work has performed on those kind of like anodes or Petri particles, which is just anisotropic, or so that by itself it creates an isotropy. You can perform any directionality, but here the interesting thing that we wanted to mention that it was even might be the case for the isotropic particles or like spheric particles. So.
Okay, so with the
even when particles have like a spheric type of symmetry, type of potential reports, and even the particle itself, they can form this type of class.
Yeah.
But that is something that it induces anisotropy by itself when you have different type of particles.
Okay, then I have a question on paper 1, I think it was.
Mm-hmm.
So you've done electron microscopy here as well.
Mm-hmm.
So why did you do TEM, transmission electron microscopy?
We wanted to look into the shell. So before that, we treated with SEM that we couldn't see because that is like a surface morphology. So we wanted to look at the graph because even the other characterization that we could use, it wasn't kind of reliable results. So we wanted to see exactly, visualize the graph. So and we treat the particle before, even in that work, the first work. So for the like even microscopy, we treat them with this osmonium, like a solution to kind of change the contrast, and then once you get that, you could image them.
And why did you embed them and microturn them?
It was something to do with reaction with this because the peg couldn't be like it would be seen. So then they did. This can like a reaction to increase this contrast with polystyrene to be seen. This is based on the reference. So
did you try visualizing them without slicing them, or just the same work?
We did see, but I mean, the thing is, we could see these coarser particles, but we weren't sure that this is just a matter of amount of that it's to the outward is just reduced amount, or is just the effect of the peg contrast. So we could see this like a core shell particle for even without that. But based on the reference, they mentioned that this is the best, like the better way to do this contrast effect, and then the peg layer can be seen than before.
Okay. Okay. But if you could see them in a normal without.
I mean, even without that treatment, you could see this corona.
Yes. So I think it sounds.
But we weren't sure that. Yeah, we weren't sure that is indication of peg grafting. So based on the reference, to see like a better contrast, to kind of make sure that you refer to the peg grafting with this contrast. We did that treatment before to see that.
Okay, and then I'd just like to go back to the experiments that Johan was talking about that's not in the paper.
Mm-hmm.
So, and this is about this capillary-induced phase separation in porous environments.
Mm-hmm.
And I don't really understand this system. What is it that you have here? What is it? What you talk about silica rods and hollow silica rods?
Mm-hmm.
What is it?
So we have like a polymer solution to see how the phase diagram look like, to creating the bulk LCC. And so we had that we could create this phase diagram without adding the particles. So, but to see effect of capillaries like created by this silica rods, we could have spheric particles, or we could have these rod-like particles. This is just a pellet that you make, but we thought maybe we can create more surface with rods.
So it's silica rods, solid silica rods?
Yeah. But hollow silicas.
Hollow silica.
Yeah, they're hollow.
Yeah, so it's like macaroni.
But it's just a small, but it's like a rod.
It's okay.
Silica rods.
Is that something you purchased?
Yeah, we bought them. We could buy them.
So what's the size?
The diameter was a few nanometers, maybe 8 nanometer. The diameter.
Okay.
But the length it was maybe even deeper.
So it's not mesoporous silica material you're talking about?
It is mesoporous. It was mesoporous silica we could get.
So this is a mesoporous silica material.
Mm-hmm.
So it's not tubes of silica.
It's like tube, but
it's a material with lots of pores.
Mm-hmm.
So it's not one tube.
But it's one tube. I mean, it's one. You mean if it is interconnected or not? You mean that thing? It's referred to as mesoporous silica, but
so
silica rods.
You have mesoporous silica particles with tubes in.
I would imagine so.
Yeah, but it doesn't.
You can't see the tube.
You can't. So these are rods, and then inside there you have pores. Is that what you're saying?
Mm-hmm. Okay. Yeah, it's hollow.
So it's a lot of small.
Mm-hmm.
So
pores.
Each of these cylinders that you draw here
mm-hmm.
contains a lot of pores.
Mm-hmm.
Okay,
mm-hmm.
now I get it. And those
that's actually an interesting question. Maybe that was the reason why we didn't. We didn't get this shift to the lower. Maybe the surface wasn't high enough. The surface created by this, because this has like a radius gyration polymer in order to penetrate to this, to reach the surface. Maybe maybe that was, yeah. This is in progress, the work. We need to image the particles, see how they look.
Okay.
Now to see.
And then you talk about two different silicas, right? If you look at the figures 514 there. This is the intensity of the animal.
Yeah, the peaks.
And then there are two different silicas. So.
No, just one, the bulk and silica. First bulk and then.
Okay, so but if you look at the figure in the lower left corner, there you have two silica. Is that two different materials?
No, it's just a different sample because it wasn't quite consistent, the result. It wasn't reliable. So we just tried to see if they reproduce the same result. So we did did the measurements several, and to see how it behaves. There's like a bulk in the silica.
I think I'll stop there.
Thank you.
And you?
That's my turn.
Yeah.
Also like to thank you for a nice discussion here, and it's nice reading. It triggers a lot of interesting questions, but I will try to keep it short. First, I would just like to sort out one thing for myself. So when we start with these particles and they aggregate together, do all particles aggregate, or is there a exchange of monomers with this, or just everything ends up in an aggregate? All particles ends up in an aggregate or string or whatever.
You don't have, you mean, by monomer you mean one particle?
One particle which is not part of an aggregate. Do you have free?
That is like a phase diagram that you create. Depending on the concentration of particle or polymer, you could create a different coexistence, either one phase or different phase, depending on that. This is like a equilibration, so you can create different type of aggregates.
So you have an exchange of particles which are free and aggregated. All were sort of aggregated.
Usually, I see what you mean. Usually, it's a bit different. For particle, once the cluster form or aggregates, it's easy for particle to enter this aggregates, but it's the other way. It cannot leave. It's usually because of the energy difference, like a barrier height, or it can be the repulsion that gets, or the minima that they trap. If it's the other way, it's not possible.
So I was thinking about it. So the residence time for one particle in an aggregate is very, very long.
Yeah,
Okay, that's fine. So then I was wondering about when you prepare the samples for the confocal microscopy experiments. You described that you centrifuge them and then you dilute samples. Was that
before you treat the particle to purify them? To stabilize the particle within water.
Before aggregation.
But that is the first process temperature, so you need to treat them. So
okay, so that's just the pre-treatment.
Yeah, so you treat them, and then once you image, you could get the results you want.
Okay, then I understand. And in those confocal microscopy experiments, there's no risk that you have a lot of aggregates absorbing to the walls.
I'm not sure. The right way to do the experiment is you synthesize the particle, you to treat them, purify the particles with different technique, dialysis or whatever.
But these aggregates that you study.
You have a good volume, so the quantity is good enough to see how they behave, not near the surface, but within the bulk solution. So.
Yeah. was also just thinking a little about how, if you have one of these very string-like aggregates, how similar to a polymer chain are they, if you describe them in terms of a polymer? Persistent length or
you mean how we characterize or like make similarity with particle? And once they form, they can stay there, the particle forming this polymer. I think we could find like using like a paper making company. They have this kind of complex to purify water, even with this kind of polymer like particle, even particle not polymer. So it can, once they form, they can remain, so you can just separate them and use them further for different usage or application, whatever. But they can form like a linear type of, and then you can just characterize the size based on the radius of particles, so how many of those particles.
But they are sort of like a flexible chain.
I guess they should be flexible.
We can sort of rotate around.
I mean, the thing is, we have here like we kind of look at the equilibration. You don't have it in flow to see what is the effect of other forces or like a tension on this particle, how they react or how to respond to this tension. Maybe that's, but I mean, the minima is good, like low enough to keep them attracted, but I don't know how they respond to the flow or like other tensions. But once you add it to or use it, but I guess at least the equilibration, they should remain even without those effects, I guess, because of the minima, which is quite several, the magnitude is quite high to keep them as they are in the.
Okay, just one more last thing. I've been working quite a lot with the oppositely charged system where you have, let's say, cationic particles and negatively charged polymer chains. They also, at least you can imagine that you have this type of potential with the attraction and a long range repulsion. But most of those systems has been studied, at least the ones I've studied, quite a different scale of much smaller particles and so on. So would you think that this type of string-like aggregates would show up in those systems in the values? Or if they do not,
I think the volume fraction of particles should be like a low.
Let's say we have very low.
Otherwise, you have different. You get different repulsion from others, like other particles.
Yeah, but if you discuss it more in terms of the size of the particle relating to the range of the attraction and the repulsion that you have. I guess in those cases, you can have a short range attraction due to polymer.
The thing is, they need to pass this barrier height because that exists, at least for this type of linear polymer-like cluster. You need to have that barrier. So for that barrier, it would be hard to pass the barrier height. So you have it there. And once they pass with equilibration with the surface, then you can, once they reach the minimum, they can there. But it would be hard to pass that barrier height from the first stages even.
Apparently they pass the barrier because they can form very concentrated phases. But if you would have them stick together in a dilute solution, then I would imagine that in this case the particles are very small compared to the range of the attractive force.
You need to have this diviolent long enough to push them to the sides. So once you create this barrier, the barrier height, so this is the initial step that they once particle approach, so you feel this barrier. The length,
the range of the attraction.
The range, I mean, once they pass the barrier, then you can, you increasing the width, you can just change the, like, yeah, it might be even thick that we, in the work, we just did focus on the width, how they, in the simulation even, you can see how they form the cluster. So that is different. So initial step is the barrier, right? Yeah, that should be fine. And then once they reach then the effect of width, it's unbranching or like how thick the cluster. Like, and they should. But to the initial step, so it's the barrier. So that they should pass the barrier, the height and the violence.
I'm happy with that. Thank you.
Okay, I thank everybody. So then it's open for the audience to pose questions. I don't seem to have any questions on the chat or on email or SMS. Do we have anything from the audience? Yes.
Okay, I have one question. Maybe the most complicated one. I don't know. So I want you maybe try to remember when you've been passing through your PhD.
Yeah, I should think.
You will have to think a little bit.
Yeah, I know.
So in order also the audience to know more or less what we are doing, I have a presentation. Yeah, I send it to Jan. So this is a timeline. So like your PhD, right? First year, second year, until today. So this starting. Okay. So the first, well, maybe you can be in this side. Yeah. So I want you first to remember when during your PhD you were the closest to have, in this case, a physical combat with your computer.
You mean what is
like a fight with your
maybe
computer?
Just a keyboard.
Yeah. Have you ever wanted to do that too?
No, I didn't use that experiment, so.
Now you never get crazy with during simulation.
I usually care not to throw something or when I get mad or something.
But the closest, you don't actually have to do it, you know.
I don't usually do physical things.
No, but it says closest. It doesn't mean you have you need to do it. So you have the picture and you have to stick it more or less when. So if you can remember one episode, like you said.
The keyboard and the screen, you mean?
No, like the situation. That you get mad with, I don't know, your simulation.
Yeah, I would have it after here, first year.
Okay.
I'm not sure, but the process, but I hope I can get it right. What do you expect?
Yeah, more. Okay. So maybe one, you literally run out of ideas and you're like, oh, I don't know. I've lost
ideas again first year. I will do it here. It's good with ideas. Run out of ideas.
Okay. The closest to burn the lab.
Again, first year.
Okay.
These are just, I hope this is just like something with the first year. Or maybe, yeah, even further to the year after.
So your grade is a 6.
Success this year.
This year, okay.
Today.
Okay. So feel ashamed of your colleagues.
Yeah, today I will feel that it should be honest work.
So having a coffee intoxication.
Yeah, this year. Yeah, I'm not sure about this, but anyway. Let's see if we have some. Yeah, the Nobel Prize, I'm quite sure.
Close
It's something from the first year to third year, but maybe we can put it.
No, I have no.
Like a Nobel Prize. Yeah, I refer to Nobel Prize last these years.
So closest to the IG Nobel Prize, which is kind of the opposite. I like the full one.
Oh my God. Maybe I don't have that much space left, but something toward the first year.
Okay, closest to be back on nerves. And super nerves.
Nerves, again, yeah, this is something with first year, but I have left just with this year's.
Okay, so the last one, and maybe the most important, the closest one to be awards is a PhD. Definitely should be this year, I guess.
Be awarded?
The closest, I guess, maybe today.
Yeah, it was today, but yeah, I will just. No, it should be honest.
Yeah. Okay. Yeah, that was all. I'm satisfied. I think you answered all the questions. So.
Yeah, but I will have. Yeah, you can keep it on the.
Okay.
So, thank you. Any other questions? If not, then we close this part of the ceremony, and then the committee and the opponent and the supervisor follow me up to the department, and the other ones up to the kitchen, the department, and there will be a small celebration. Okay.
Thank you. Thank you, everyone. Iria, maybe you can remove it.